So last week, we talked about graphing a couple of different days, okay? And we did our lab on position versus time graphs, which remember is due on May the 10th. So make sure you have yours ready for that day, okay? Things we talked about with position versus time graphs. So on a position versus time graph, you will have time in whatever units. I wrote seconds here, okay? And you have position in meters. Okay, so we got our position in meters, we got our time in seconds here, okay, and we were talking last week about if we had a linear fit, kind of like what we got on our graphing lab, okay, that when Google Sheets would spit out the equation, it would be this, y equals mx plus b, except there would be numbers in for m and b, right? There'd be no numbers in for y or x because they come from whatever point you've picked on the line, okay? What were we calculating when we solved for the slope of this? We went y minus b over x. Right, okay? The slope of this line represents the average velocity of the object. Okay, now that's all well and good if your graph is one linear line. Okay, but on this graph, obviously it's not. Okay, so we may have to delve into our formulas a little bit. That's v equals d over t. Okay, and use that a little bit, and also this one, right? And that is that displacement is final position minus initial position. And that's, of course, where this formula equates to this, okay? Velocity is displacement, which is final position minus initial position, divided by time. Y would be our final position, B would be our initial position, and X would be our time. Okay, so that's where those two formulas go together. Is that ringing a bell from last week? Okay. All right, so on this particular graph here, obviously I'm not going to use any of this slope stuff, okay, because I don't have one single line on this graph. So it says we want to calculate first the total displacement. So that means I'm going to be using this formula here. Displacement is final position minus initial position. According to my graph, my final position is 0.5 meters. And my initial position is 0.2 meters. All right, so if I want to find my displacement, okay, PF minus PI, that'll be 0.5 minus 0.2, so my total displacement is positive 0.3 meters. Why did I write positive on there? It's a vector quantity, okay? Since my graph doesn't go down into the negatives, but doesn't give me any other directions, it doesn't say north or right or left or whatever, okay? I'm just gonna write positive because that's the best direction that I can give in this situation, okay? Questions on how I did part A? Okay. All right, for part B, okay, it says it wants the total distance traveled. All right, now I can't go final position minus initial position on this because that will give me the displacement. What I need to do is figure out how far it went in each section of the graph. How far does it go in this section of the graph? That's where it is. How far does it go? It doesn't go anywhere, right? Okay, it's at position 0.2 and at, again, position 0.2. It didn't go anywhere. The position didn't change. That's why it's a flat line. Okay, in this part of the graph, we go from 0.2 to 1. So the distance traveled in that part is 0.8. Okay, how far does it go in the flat part? None. All right, so we got a 0 there. And then it goes from 1.0 back to 0.5. Okay, since distance does not require direction, it's a scalar quantity, I just add these two numbers together and my total distance ends up being 1.3 meters. Okay, everybody all right with that? Okay, now the other two just involve using either V equals D over T or V equals D over T. All right. I'm trying to find in part C average velocity, so that means I want to use this one, right, where I use the displacement divided by the time. All right, so to calculate average velocity for this question, that's going to be positive 0.3 meters, because that's what our displacement was, divided by, this took 7 seconds. Actually, I got the answer right there, so I don't need to plug it in. All right, so that's going to give me positive 0.04 meters per second. Again, velocity is a vector quantity, and it has to have the same direction that our displacement has. Hey, everybody all right with that? Okay, so we were talking on Friday about how a graph is a visual representation of a word problem. Okay, so this word problem would have probably sounded something like this. An object is stationary at a position of 0.2 meters for 1 second, and then moves at a constant velocity of, I don't know what the velocity is in that section there because I didn't calculate it, but be 0.8 meters per second for 0.4 meters per second for 2 seconds, and then stops and then does this. Okay, like we could easily translate this into a word problem if we wanted to. Okay, this is a visual representation of that. 7 seconds, right here, right? So this is 5, 6, and 7 seconds. Yep. All right, the last part says it wants the average speed. We calculate average speed by distance over time. I already calculated the distance. It's 1.3 meters divided by 7 seconds. Okay, so that'll give us 0.19 meters per second as the average speed over the whole trip. Okay. So really, there's no new math now that we're dealing with graphs. It's the same math we did before. Okay, it's still V equals D over T. Okay, any questions on number 1? Okay, in Google Classroom, you will find the workbook package for this unit. Okay, it's in the classroom stuff here. So I go to Science 10, I go to Classwork. Okay, you'll find it here under Course Materials Physics. Okay, and you want the one that says Worksheet Package. I'll put it up on the board as well, but in case you want your own. Okay, and we are looking at page 4 because we already did that one. Okay, so we're looking at some of the questions here. Okay, on page 4, all right, starting with number 2 there. Okay, and you can move on to number 3 if you get done number 2, but I'll give you guys a little bit of time there to get ahead of me, and then we'll walk through these ones as well. So for question number 2, okay, we again have a position versus time graph, and just for kind of review's sake, what is the object doing between 0 and 40 seconds? Starts at a position of 0, and by the time it gets to 40 seconds, it's 400 meters from where it was before. Not during that section, no. At 40 seconds, it stops, yes. Yeah, it's going to that position, right? It's doing it at a, not acceleration, positive, yeah, velocity or speed, either one. Yeah, it's traveling at a constant velocity during this part. How do we know that? Because every second it goes up by the same amount, or every 10 seconds on this graph goes up by the same amount. That means it covers the same amount of distance every second. That's a constant velocity, constant speed. Okay, so for question A, it wants to know the distance traveled between 0 and 90 seconds. All right, so 90 seconds is right here. All right, so we want to find the distance traveled between 0 and 90. So in this first part here, we go 400 meters. How far do we go here? None, okay, because it's flat. And then we go from 400 back to 200. So this is 200 meters here. So our total distance between 0 and 90 seconds is 600 meters. Okay. Questions on part A? Okay. So for part B, they want to know the displacement from 20 seconds to 80 seconds. So we have to remember that we calculate displacement by going final position minus initial position. So I've got to find those two positions. All right, my final position is at 80 seconds. So at time 80 seconds, my position is 300 meters. Okay, my initial position is at time 20. So that's 200. Okay, so my total displacement there, okay, would be positive 100 meters. Everybody all right with that? Okay. They want to know the speed over the whole trip. Okay, so speed over the whole trip means I'm using this formula. Speed equals distance divided by time. Well, the total time's 100 seconds. I can read that right off the graph. Okay, my total distance is that I went 400 up and then came back all the way. Okay, came 400 meters back. Yeah, I did it at two different velocities. That's fine. I still went in the end from positive 400 back to 0. So the total distance traveled is 800 meters. Okay, so that's going to mean 8 meters per second. Okay, and no direction on that, no positive on that because that's speed. Okay, speed is scalar. And then they want to know the velocity over the whole trip. That's easy because velocity is displacement divided by time, and my final position and initial position are the same. That means I came back to where I started, and that's exactly what that graph says. So my total displacement is 0, thus my velocity is also 0. Okay, that's what we got. Okay, any questions with that one? How many people have done number 3? Okay, I'll give you a few more minutes on number 3, and then we'll have a look at that one as well. Yeah, just keep going until you get to the, or sorry, no, stop, because at number 4, we're getting into velocity versus time graphs, and I want to do that one together to review velocity versus time graphs. So if you're already done number 3, okay, don't worry about number 4, or you can try it if you want. If you think you know how to do it, go right ahead, okay? But we want to make sure we get a chance to talk about it as well. Okay, so for number 3, we're going to be asked to do similar calculations here, except this one starts out going which way? Backwards, yeah. Okay, it starts out going in a negative direction at a constant velocity still. It's still a diagonal line, okay, but it does end up or start out going backwards. Then it stops for a little while, and then it moves forwards at a constant velocity. All right, so as long as we can interpret the graph, it's always important to look at a graph and be able to interpret what's going on. Okay, so for part A, the displacement from 0 to 4 seconds. All right, so again, the formula for displacement is final position minus initial position. So our final position is negative 4 meters. Our initial position was 0. Okay, so our displacement there is negative 4 meters. Okay, pretty simple calculation for part A. For part B, the total distance traveled. All right, so that means we got to find all the sections again. We know that the first one is 4 meters. Okay, again, we don't care which direction because we're looking for distance. Doesn't go anywhere during this part, and then it goes from negative 4 to 6, which is 10 meters. All right, so our total distance then is 14 meters. Okay. For part C, average speed over the whole trip. Okay, so speed is distance over time, and I just calculated the total distance to be 14 meters. All I have to do is divide that by the total time, which is 6 seconds. All right, so 14 over 6 should give me 2.3 meters per second. Okay, no direction on that because it's speed and it's scalar. All right, then lastly, we want the average velocity over the whole trip. Okay, so average velocity is displacement divided by time, and that means final position minus initial position divided by time. We already know the time is 6 seconds. Okay, so we can put that in right now. Then I've got to do this calculation. Final position, positive 6. Okay, minus our initial position, 0. All right, so it's 6 over 6, which is an average velocity of positive 1 meter per second. Okay, so nothing's really mathematically difficult. We just have to get the hang of how to get the things off the graph that we need. Right? That is also the case when we are dealing with velocity versus time graphs, which is what we're going to look at with question number 4 here coming up. Okay, because question number 4 is a velocity versus time graph, so it's showing us a much different perspective on the motion than a position time graph does. Anyone need this one anymore? Okay, so on number 4, now that this is a velocity versus time graph, I have to understand it is showing me how fast and in what direction the object's going, not where the object is. All right, so in the first part of this graph, it's telling me that the object is doing what? It's not doing anything. Okay, it's moving at a constant velocity of 0 meters per second. Okay, and it does that for 2 seconds. Then what does it do? Okay, it is going backwards, but what kind of movement is it? Is it constant velocity or acceleration? It's acceleration. Remember, this is a velocity versus time graph. This is telling me the object increases its velocity from 0 to -3 meters per second. Okay, it's not telling me where the object is anymore. Now it's telling me how fast it's going. It's changing its velocity. That's an acceleration. Okay, then between 5 seconds and 7 seconds, it accelerates in the other direction and changes its velocity from -3 to +2 meters per second. So it accelerated positively. All right, what does it do between 7 and 12 seconds? It stays at a constant velocity, right? Its velocity does not change, but it is traveling at a constant velocity of 2 meters per second during that time. Okay. After that, then it accelerates again. Anytime we got a diagonal line, the velocity is changing, and any change in velocity is acceleration. It accelerates from +2 to -6 meters per second, so it's accelerating backwards. And then it abruptly accelerates forwards. Does it move forwards? No. That's the weird thing. I can accelerate forwards while moving backwards. Right, I'm just slowing down. Right? When I throw something up in the air, it moves upwards, but accelerates downwards. Okay? So it's possible for acceleration and velocity to have opposite directions. Okay? All right, what's going on in this little flat part here? Staying at a constant velocity of -2 meters per second, then accelerating to a stop. Yeah. Okay. So it's slowing down, okay, and reaching a velocity of 0 and staying at that velocity of 0 for the last second. All right. So if I want to calculate acceleration, and we only talked about this briefly last week, the formula for acceleration is Vf minus Vi over t. Okay, that's on your formula sheet, but that's the formula for acceleration. This is where we get it from. If I have a velocity versus time graph that looks like this, okay, and I get an equation like this, okay, the slope of this line is going to be this formula, right? Because it's going to be m equals y minus b over x. Y would be our final velocity. B would be our initial velocity. X is once again our time. Okay, so that formula is the slope of a line on a velocity versus time graph, same as it was for velocity on a position versus time graph. Okay. All right, so I've got this formula here. Because I've got a bunch of different sections, I'm not going to be doing any slope calculations. Okay, I'm going to be doing this section by section. All right, so I want to find the acceleration between 12 and 14 seconds. So I need to know my initial velocity and my final velocity. And then I just need to plug in the numbers. Okay, so Vf is -6 minus 2 divided by 2 seconds. Right? It's between 12 and 14 seconds. So -6 minus 2 is -8. Divided by 2 is -4 meters per second. What were the units? Remember, this is meters per second, and I'm dividing by seconds. So it's meters per second squared, meters per second per second. Okay, those are our units for acceleration. Okay, so remember when we do this, meters per second divided by seconds, we're calculating meters per second, which we write as meters per second squared. Okay. Doesn't mean the number is squared, just the units. Okay. All right, for part B of this question, they want to know the total displacement over the whole trip. Now this is going to take us a while. All all right? Because we had said to calculate displacement, we were going to have to take the average velocity and multiply that by the time. Essentially, we're using this formula here, right? Average velocity is displacement over time. We're just manipulating for d. All right. I have to do that for each section of the graph, though. Okay? Because, yeah, it's a lot of areas. Exactly. Remember, we said it's calculating the area under the line. So I've got a bunch of triangles, and I got a bunch of rectangles and things like that I've essentially got to find the areas of. So my best bet would be right now is to just kind of draw all of those. Okay, is to draw all of my areas. Okay, so I've got a triangle here. Okay, I can do that one. I've got a triangle here. I've got a triangle here. This rectangle. Okay, I've got this triangle here, and this little one. Okay, or I could just do one big triangle. That might be faster. Doesn't really matter which way we do this. I could just do this triangle, and then I would have that triangle there, and something like that. Okay, so those are the shapes that I have to find the areas of. Okay, and find that's going average velocity times time. All right, so for this triangle here, I've got a base of 1, 2, 3, 4 seconds and a height of -3. Okay, so -3 times 4 seconds, that's -12. Okay, sorry, over 2 because it's a triangle, right? So -6. All right, then I've got this tiny little triangle that's got a base of 1 second and a height of 2 meters per second. Okay, so that'll be 2 divided by 2, so this one is 1 meter. -6 meters. Okay, then I've got this rectangle that's 1, 2, 3, 4, 5 wide by 2 high, so that's 10 meters. I've got this little triangle that's only half a second wide. Okay, so 2 times 1/2 is 1, divided by 2 is 1/2. Okay, then I've got this long skinny triangle that's 1.5 seconds on the base. Okay, and it's -6 high, so -6 times 1.5 is 9, divided by 2 is 4.5, but that's negative. Okay, what? With my hat? Oh, because it shines off, but it's my Gord Downie hat. It's very Canadian. You guys know who Gord Downie is, right? If you do, oh God. The Tragically Hip? You don't know? Oh my God! You call yourself Canadian and you don't know who the Tragically Hip are? Oh. Okay, we're gonna fix that in a minute. First, we got to finish the graph. My mind is blown now though because you guys don't know who Gord Downie and the Tragically Hip are. But okay, all right. So we've got this triangle here. Okay, this next one here. The height of that triangle is 4, and it's 2 wide. So 4 times 2 is 8. Over 2 is -4 meters. Then I've got this rectangle that's 1, 2, 3, 4 by -2 high, so that's -8 meters. And then I've got this little triangle here that's 2 high by 1 second, so that's going to be -1 meter. All right, now I've got all the displacements. What do I do with them? Add them all up. Okay, so we've got -6 plus 1 plus 10 plus 0.5 plus -4.5 plus -4 plus -8 plus -1. All right, so our total displacement is -12 meters. Okay, and that's what we got here. A lot of work for that answer. On a test or a quiz, I probably wouldn't give you a graph with that many shapes. It would be like one triangle and one rectangle or something like that, just to show me, hey, I know how to do this, Coderre, but yeah, I don't have a half an hour to find all the shapes. Okay, everybody all right with how that works? Okay, so area under the line is the equivalent of going displacement is average velocity times time. Remember, the reason for that is this. Okay, during, let's say, this part here, The object is accelerating. That means its speed is changing or its velocity is changing. So I want to find the average velocity. Okay? Well, the average velocity is halfway between its initial and final, because half the time it would be going slower than that and half the time it would be going faster than that. Okay? That's why when we calculate the area, we go base times height over 2, okay? The height over 2 is calculating the average velocity. The base is the time. Okay, so that's what we're doing when we're calculating the area under the line, is we're essentially taking average velocity times time. Okay, C, average velocity over the whole trip. Okay, well, I just calculated the most difficult part of that, which was the displacement. Okay, remember, if I want to calculate average velocity, I need the total displacement divided by the total time, and the total displacement is negative 12 meters. The total time, 20 seconds, okay? That's why we get negative 0.6 meters per second. Yeah, let's say for now, I mean, we haven't talked about significant digits yet, and I don't think we will. You learn about that in Physics 20 and Chem 20, where, yeah, our measurements, our calculations can make our measurements more accurate, but we're not going to talk about that in Science 10. Let's go, yeah, 1 or 2 decimal places I'm not worried about. Yeah. Okay, and then for part D, okay, we're looking for the average acceleration between 14 and 20 seconds. Okay, so here's time 14 seconds right here and 20 seconds. All right, so again, average acceleration is this formula here, VF minus VI over T. All right, so my final velocity is 0. My initial velocity is -6, and that takes 6 seconds. Okay, so I have 0 minus -6 is 6. Okay, divided by 6 is 1 meter per second squared, positive 1 meter per second squared. Okay. So this is just a lot of plugging numbers into formulas. It is. Yeah. Okay, and then lastly, the average speed over the whole trip. Okay, so for that we need the total distance traveled. Did I already do the bulk of the work for that? Yes, I take all those numbers except none of them can be negative. Okay, so I take all those numbers and I just add them up. All right, so I'm going to have 6 plus 1 plus 10 plus 0.5 plus 4.5 plus 4 plus 9. Okay, so my total distance is 35 meters. That took 20 seconds. All right, my average speed is 1.75 meters per second. Okay, making sense? Right. The velocity versus time graphs, there's more work on those, okay? Because you usually end up doing these area calculations, so it takes longer. Okay, let's have you guys work on a couple of velocity versus time ones here. So we just did number 4. So let's have you look at 5 and 6. Don't worry about the curves on here. Just imagine that these are straight. I just couldn't find a graph where they were straight. Okay, so don't worry about the curves. Just imagine it's perfectly straight. Okay, and this, so that straight line there would go straight to 5 seconds, okay, and then go up to 15 seconds here. Okay, so just imagine it's all straight. All right, so on number 5, okay, we've got an object that starts out traveling at a constant velocity of 8 meters per second, negative 8 meters per second. Then it accelerates, okay, positively to a velocity of 8 meters per second, okay, and then travels at 8 meters per second for the next 5 seconds. This isn't one of the questions in there, but I'm going to ask it anyway. At what time does the object change directions? Yeah, at 10 seconds. Okay, now a lot of people will instinctively say that it changes direction right here. The problem with that is that it's still traveling backwards here. In fact, it's traveling backwards as long as the line is below the x-axis. It only changes direction when its velocity becomes positive, which is at time 10 seconds. So even though here the acceleration went from being 0 to being a positive number, it didn't actually start moving forwards or in a positive direction until 10 seconds. Okay, so essentially this is a graph of somebody walking backwards or running backwards into a bungee cord. Okay, so if there was a bungee cord stretched across the room, I'd be running backwards. I hit the bungee cord and it starts accelerating me forwards. Okay, I slow down, stop, and then the bungee cord shoots me forwards again. Once I leave the bungee cord, then I walk forwards at 8 meters per second after that. Okay, everyone kind of follow me there? All right, for part A, they want to know the total displacement over the whole trip. So we got to do our shapes. Okay, we've got to find the area here, the area in this triangle, and similar thing here. So we got this triangle and this rectangle here. Here's the good news. The parts below the line and the parts above the line are the same, so we can save ourselves some math. Okay, so we got -8, and that goes over 5 seconds. So this area here is -40. This is -8 times 5 over 2, so it's -20. That means that this one is 20 and this one is 40. What's our total displacement? 0. Okay. If I did exactly the same thing above the line as I did below the line, then I've got to end up back where I started. Okay. Average acceleration between 5 and 15 seconds. So that's the diagonal part of this. All right. Remember, our formula for acceleration is final velocity minus initial velocity divided by time. Well, they told us that the time is 10 seconds, so I can write that in right now. My final velocity is positive 8 meters per second, and I'm subtracting -8 meters per second. So 8 minus -8 is 16. All right, so 16 over 10, that's positive 16, over 10 gives me an acceleration of positive 1.6 meters per second squared. Okay. All right, then the average speed over the whole trip. Have I already done the bulk of the work for doing that calculation? Yes, I have. Okay, average speed is still calculated by going distance divided by time. Okay, my total distance is 120 meters because I went 60, then I went 60 again. Okay, so 120 meters, okay, divided by 20 seconds gives me an average velocity of 6 meters, sorry, an average speed of 6 meters per second. No vector on that because it's scalar. Okay. How are we doing on number 6? How many people have done number 6? Okay, I'll give you a few more minutes on number 6, and then we'll talk about that one as well. If you're done number 6, keep going. I'll make 6 bigger. Now, it's hard to read 6, so I'm going to try and help you out a little bit here. Okay, just so you can kind of read when those times occur for each one of those. All right, so for number 6, for part A, we're calculating acceleration, so we're just using VF minus VI over T here, okay, and that is between A and B. So we have a time of 2 seconds, and our final velocity is 20, our initial velocity is 0, okay, so our acceleration there is positive 10 meters per second squared, okay, pretty straightforward on that one. Okay, calculating the displacement between A and E, so I've got to go all the way to 8 seconds, right? So the way I would do that is I would say I would go big rectangle, okay, that would encompass basically all of this area here. I would have that small triangle above it, and then I would use this big rectangle here, okay, as my other area, kind of limit my calculations. The fewer shapes I can draw, the less stuff I have to calculate. Everyone all right with that? Okay, so my first triangle here has a base of 2 and a height of 20, so 2 times 20 is 40, over 2 is 20 meters. Then we've got this rectangle that's 3 on the base and 20 high, that's 60 meters, and it's positive as well. In fact, they're all positive. And then I've got this small triangle that has a height of 20 and a base of 1, so it's going to be 10. And then I've got this big rectangle here that's 3 on the base and it's 40 high, so we're looking at 120 meters there. Okay, so when we add those all together, we got 180 plus 30 is 210. 210 meters is our total displacement, and that should be positive. Should be a positive on there. All right, questions on B? All right, for C, acceleration between F and G. All right, so that's not going to require very much calculating, because what's the object not doing there? It's not accelerating. Okay, the velocity stays constant between F and G. All right, so it's 0 meters per second squared. Guys, I don't know how many times I've played that trick on people on a quiz or even a unit exam and got them on it. Okay, people just have a problem with 0 being the right answer for things. Okay, so know that that's one of the tricks I have in my bag, and I'm going to use it. So be on the lookout for it. Okay, if a question is out of 1 mark, how much calculating do you suppose you need to do for it? None. Okay, that would be a 1 mark interpretation question. Okay, you'd be surprised how many people will show me between 4 and 6 marks worth of work for that question. Okay, because they just think it's got to be more than that. All I'm testing is, do you recognize that the shape of this graph says this? Okay, it's not even that I'm testing calculation. I'm testing interpretation skills. All right, and then the last thing here, average velocity between A and F. All right, so if I'm going to find average velocity, I need the total displacement and the total time. So I already found the total displacement to E. I just need to extend it out now to F. All right, so I'm going to have an extra triangle and an extra rectangle that I just need to calculate the areas of and add it to that 210 I had before. All right, so this triangle here is 2 on the base and 20 high. Okay, so 2 times 20 is 40, over 2 is 20, and then I've got 2 times 20. Okay, so that'll be 40 there. So it's an extra 60. So we're looking at 270 meters as our total displacement. And then we're dividing that now by 10 seconds. Okay, so we get 27 meters per second. Everybody all right with that? Okay. And then lastly, the total distance traveled. Well, now I got to calculate all the rest of the shapes. Okay, there's no other way for me to do that. So I'm just going to calculate this last rectangle here and that small triangle up top. This one here is going to be another 40-meter triangle because it's the same, or sorry, rectangle because it's the same size. Okay, this triangle is 1 second high by, or sorry, 1 second on the base by 10. So it's 5. We just add on an extra 45 onto that, and we're looking at 315 meters. Okay. All right. Everybody feeling okay about those? Right. Okay. Let's see how we do with number 7. I would highly recommend getting number 7 done before the end of class because you have a quiz tomorrow and it'll be on this. Maybe this one. It might be a subtle hint.